Hi class. This section is about the idea of the mole concept, section 3.1. We've skipped over section 2.4 about molecules. And everything, of course, is connected to everything else. And we'll get back to the section 2.4. But this is about the concept of the mole. I'm not even sure that this goes about it as directly as it should. But we'll follow this. We'll see what happens. Okay. The swimming pool is an example of a complex mixture of substances that need to be carefully maintained. The formula mass and the mole concept. So we're going to calculate formula masses for covalent and ionic compounds, and then define the amount of a unit mole and the related quantity of Avogadro's number. Explain the relation between mass, moles, and the number of atoms or molecules, and perform calculations deriving these quantities from one another. Okay, we talked about the atomic weight previously of a substance, and now we're going to be talking about compounds and formula masses, which is the sum total of the atomic weights that are in the formula for that compound. Like H2O would be the 2 times the atomic weight of hydrogen plus the atomic weight of oxygen. Covalent substances exist as discrete molecules. So all this bullet point is saying is defining the word covalent. So if something exists as a molecule, that is what a covalent substance is. That is in contrast to an ionic substance, which exists as ions, and when it dissolves in water, the ions are separated from one another. The formula mass of a covalent substance may be correctly referred to as the molecular mass. Now, this is just words. You've got formula mass generally applies to everything. The molecular mass is of molecular substances, substances that form discrete bonds between the atoms, like H2O or sugar. But the contrast is to ionic substances like sodium chloride, like salt, that does not exist as a discrete molecule. And then you have to fall back to formula mass. And you could still say the atomic mass is the formula mass for the oxygen, for the atom. So anyway, you've got atomic masses, formula masses, which are generally applied to ionic substances. Of course, it also applies to molecular substances, but if you say molecular mass, it does not apply to an ionic substance. Okay, so here we have carbon tetrachloride. I'm sorry, we've got chloroform, excuse me. Carbon with a hydrogen and 3 chlorines. So you take the 3 chlorines with this atomic weight equals 106.35. The hydrogens, which is only 1.008, and the carbon, which has an atomic mass of 12.01. Now note, these atomic masses reflect the natural abundance of the isotopes. So most of the carbon that exists is carbon-12, which is defined as an atomic mass unit of 12. plus a tiny amount of carbon-13, which increases the the atomic weight as it appears on the periodic table a little bit. Anyway, so we have these atomic weights times their the numbers in the formula, the number that goes into the formula, and we add it all up, and that is the molecular weight or molecular mass of the molecule of chloroform. The average mass of a chloroform molecule is 119.37 atomic mass units, which is the sum of the average atomic masses of each of its constituent atoms. The model shows the molecular structure of chloroform. By the way, all those different isotopes will show up in an analytical technique in the future known as mass spectra. And so each one of the individual masses that make up this average mass can be seen in a mass spectrum. The average mass of an aspirin molecule is 180.15 atomic mass units. This model shows the molecular structure of aspirin, C9H8O4. So 9 times the atomic mass of carbon, 8 times the atomic mass of hydrogen, and 4 times the atomic mass of oxygen, all total gives you 180.15. Now, okay, this one is interesting. They didn't name this one. So this is an acid, methyl group. I believe this is naproxen. Not naproxen, ibuprofen. This is ibuprofen, but they don't name it. Well, let's see, back up. No. So this is ibuprofen. This is the isobutyl part of it, and this is another part of it. Pardon my dog. And my cat's going to bother me too now. Okay. All right, get down. Ionic substances are composed of discrete cations and anions combined in ratios to yield electrically neutral bulk matter. Ionic compounds do not exist as molecules. The formula mass for an ionic compound may not be correctly referred to as a molecular mass. The average atomic masses of the ions can be approximated to be the same as the average atomic masses of the neutral atoms. Okay. The ions, of course, have lost an electron, and of course it goes from one atom to the other, so the electrons are still there, and so when you calculate the mass of the overall formula, which is neutral, using the atomic masses is correct, even though an electron has gone from one atom to the other, creating a pair of ions. So table salt contains an array of sodium and chlorine ions in a 1-to-1 ratio. So 1-to-1 is the formula for salt, that is 1 sodium and 1 chlorine, hence formula mass. And the formula mass is 58.44. I want to add something. We're going to get to the concept of a mole. And every time we use the term AMU, we can always replace that with grams per mole. Just remember that. That's where we're going with this, is that this will be a conversion factor for us for going from grams to moles. I don't have the cartoon, but a long time ago, the American Chemical Society had a cartoon where there were all these grandmas on rocking chairs going into a machine, and out the other end of the machine had moles jumping out. And the machine itself was labeled with divide by the molecular weight. So to convert from grams, grandmas, to moles, the little animals, divide by the molecular weight. So this is another substance, aluminum, sulfur, and oxygen. I'm not familiar with this compound, aluminum sulfide oxide. Not familiar with it. Aluminum oxide is a well, aluminum is found a lot in clays, but I'm not familiar with this compound, and so it's giving a molecular mass. So this is saying that this thing actually forms molecules. Okay. I think it really should have been labeled as formula mass. The mole is the amount unit similar to familiar units like pair, dozen, gross, etc. I find my students don't remember what a gross is, or were never exposed to it. A gross is a dozen. So it's the number 144, and I've seen people with a t-shirt that says I am 144, meaning I am gross. The mole is defined as the amount of a substance containing the same number of discrete entities, such as atoms, molecules, or ions, as the number of atoms in a sample of pure carbon-12 weighing exactly 12 grams. The mole provides a link between the mass of a sample and the number of atoms, molecules, or ions in that sample. By the way, we oftentimes don't need to know the number of atoms or molecules. All we need to know is that we have a mole of that substance. And things generally react in unit quantities of moles with moles. So, like one mole of O2, of oxygen 2, will react with 1 mole of carbon to form CO2, for example. Or 2 moles of hydrogen 2, H2, plus 1 mole of oxygen sub 2 will react to form 2 moles of H2O. Those are the kind of things that chemists need to keep track of, and the mole is the unit for doing it. The fact that we have a number for the number of molecules or atoms or ions in a mole is just a nice thing to have. The number of entities comprising a mole has been determined to be 6.02214,179 times 10 to the 23rd. That's a very big number. This constant is named after an Italian scientist, Amedeo Avogadro, or Avogadro. I tend to speak things in Spanish. It's known as Avogadro's number. A curious fact is Avogadro never knew his number. Avogadro proposed a law that the same number of particles were in that two gases of the same volume at the same temperature had the same number of particles in them. That was Avogadro's law. But he never knew how many particles that was. But this has been named in his honor. So Avogadro's number is 6.022 plus some change times 10 to the 23rd. The masses of 1 mole of different elements, however, are different. Not the numbers in a mole, but the masses are different, since the masses of the individual atoms are drastically different. Okay, each sample here contains a mole of atoms. So you've got 65.4 grams of zinc, 12 grams of carbon, 24.3 grams of magnesium, 63.5 grams of copper, 32.1 grams of sulfur, 28.1 grams of silicon, 207 grams of lead, and 118.7 grams of tin. Tin is SN. The molar mass of an element or compound is the mass in grams of 1 mole of that substance. That is, this is the AMU, is the grams per mole, a property expressed in units of grams per mole. The molar mass of any substance is numerically equivalent to its atomic or formula mass in AMU. For example, a single carbon-12 atom, that 12 is supposed to be elevated as a superscript, has a mass of 12 AMU. A mole of carbon-12 atoms has a mass of 12 grams. Or to turn this around, you can say carbon-12 as a substance has has 12 grams per mole. Each sample contains, in this picture, 6.02 times 10 to the 23rd molecules or formula units, or that is 1 mole of the compound or element. So they are octanol, formula mass of 130.2, mercury iodide, which is this bright orange material, formula mass of 459.9 AMU, 32 grams of methanol, formula mass of 32.0, and 256.5 grams of sulfur sub 8. Now, sulfur itself as an element has a formula mass of 32, but you're multiplying it by 8, so you get the 256. So again, element, average atomic mass, its molar mass, grams per mole, and the atoms per mole. Of course, the atoms per mole is just a number, 6.02 times 10 to the 23rd. The molar mass, grams per mole, is identical to the average atomic mass, its AMU. So that's all this picture's really saying, is that these two are absolutely equivalent. Doesn't matter what element they chose to demonstrate that with. The number of molecules in a single drop of water is a huge number. It's 100 billion times greater than the number of people on Earth. Now, how did they get this number of Avogadro's number, this number of atoms per mole? It came from the charge on the electron. It allowed them to determine how many electrons were delivered. It was already defined. The coulombs of charge as bulk charge. Now you knew how many electrons were in that bulk charge. And then when you ran an electrolysis, it allowed you to know how much mass was transferred for how many electrons. And you had some idea of how many electrons it took to deposit one atom there. And so you not only had the mass, you had its atomic mass, and now you, in terms of AMU, and now you knew how many atoms were deposited, and all that allowed you to calculate how many atoms there were per mole. The relationship between formula mass, the mole, and Avogadro's number can be applied to compute various quantities that describe the composition of substances and compounds. According to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? So you have mass of grams, divide by the molar mass, it gives you moles of potassium. So this is converting grandmas to little furry animals. You divide by the molecular weight, or in this case, the atomic weight. Since the formula is an atom, it's the atomic weight. So 4.7 grams divided by 39.1 grams per mole. Of potassium gives you 0.12 moles of potassium, K. A liter of air contains 9.2 times 10 to the minus 4 moles of argon. What is the mass of argon in the air? I'm giving a lecture. What is the mass of argon in the air? Let's take a... Okay, I'm back. A liter of air contains 9.2 times 10 to the minus 4 moles of argon. What is the mass of argon in a liter of air? So somehow you know the moles of argon in the air. So in this case, you multiply by the molar mass, or grams per mole, and the moles will cancel out and leave you with grams. So it gives you the mass of argon atoms. Copper. So you have the mass of copper, divide by the molar mass of the copper, gives you the moles of copper atoms, and then from the moles you multiply by Avogadro's number, and it gives you the number of copper atoms. So in this case, let's see, they're not telling us what C2H5O2N is. But if I were to guess, let's see, this would be glycine, perhaps, the amino acid. So to go from the mass of this to the moles of that, you divide by the molecular weight, converting from grams to moles. Aha, glycine. So you've got copper, hydrogen, oxygen, nitrogen. You calculate the molar mass. You start with 28.35 grams of glycine. You divide by the by the molecular weight, which is 75.07 grams per mole, but that means the grams go with the number and the moles go on top, and this allows you to cancel the grams and be left with the number of moles of glycine on top. Vitamin C is a covalent compound with the molecular formula C6H8O6. The recommended daily allowance of vitamin C for children aged 4 through 8 is 1.42 times 10 to the minus 4th moles. What is the mass of this allowance in grams? The molar mass for this compound is computed to be 176.124. So you have the moles of vitamin C multiplied by the molar mass, the moles cancel, and it leaves you with the mass of vitamin C. So 1.42 times 10 to the minus 4 times the 106.124 gives 0.0250 grams of vitamin C. A packet of let me go back to that. That's not very much. That would be 25 milligrams of vitamin C. Many of the supplements of vitamin C are 500 milligrams. So that just shows you the gross excess of what we need versus what is in typical pills. A packet of artificial sweetener contains 40 milligrams of saccharin, which has the structural formula blah blah. Given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are there in a 40 milligram sample of saccharin? How many carbon atoms are in the same sample? Well, the way you would proceed is that you go from grams to moles. Of course, this is milligrams, so that milli right there means 10 to the minus 3. There you go. It's a 0.0400 gram sample. And then you divide by the molecular weight, so the grams cancel and you're left with moles on top. And then you multiply that number times Avogadro's number, 6.022, times 10 to the 23rd. All right, so boom, 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 equals 1.31 times 10 to the 20th saccharin molecules. And then you count the number of carbon atoms that are in a molecule, and you multiply that number of molecules of saccharin times the number of carbon atoms in a saccharin molecule, and you get 9.17 times 10 to the 20th carbon atoms. A typical human brain weighs 1.5 kilograms, occupies a volume of roughly 1.1 liter. Information is transmitted throughout the central nervous system by specialized cells. My specialized cells are wondering why we're talking about this. Chemical signals are transmitted from neurons to the other cells by the release of neurotransmitters into the small gaps. Dopamine is a neurotransmitter involved in a number of neurological processes. This is what was a treatment for Parkinson's disease, or it still is. So that was the end of that section 3.1. So thank you for listening. Bye.